Hello, everyone. My name is Kelly Hall. I'm a marketing coordinator for ALS North America. I want to thank you all for joining us today for our Webinar Wednesday series. Our presenter today is Tim Crowther. Tim received his Bachelor of Science in Chemistry from King's London College London in 1988 and a Master of Science in Analytical Chemistry from the University of British Columbia in 1991. He is a chartered analytical chemist with more than 25 years of experience in this field. Tim is the chairman of the BC chapter of the Canadian Council of Independent Laboratories for the Environmental and Life Sciences Division. He volunteers on the BC Enhanced Water Quality Assurance Steering Committee and is a member of the North American Metals Council Selenium Working Group. Now, Tim serves as the Regional Client Services Manager for Canada at our ALS Vancouver laboratory. And today, Tim will be discussing why Selenium Speciation is important and why it is challenging to detect. During this presentation, feel free to use your Ask a Question or Raise Hand features to ask questions either throughout the presentation or at the end. Tim, thank you for taking your time to deliver this presentation today. I will go ahead and turn it over to you.
Thanks very much, Kelly, and good morning, everyone, and welcome to today's webinar on selenium speciation. So selenium is present in naturally in many foods of both animal and plant origin, and some plants may even protect themselves from animals by storing large quantities of selenium in them. And selenium is added to fertilizers to enrich plants, as well as present naturally at higher levels in food due to both environmental and geological concentrations. So also selenium is added to various food products, including meat, chicken, pork, and beef, and also dairy products in certain countries. In Korea, there's Seleno chicken and Seleno pork, which are actually sold as premium brands of chicken and pork, and they're both fortified with a high content of selenium. So in this picture, I'm just wondering if any of you know which of these food groups contains the most selenium. The answer is actually Brazil nuts, and certain Brazil nuts from certain areas have some of the highest levels of selenium in them. And it's an interesting food group as well, because it also is on the border of what is an acceptable dosage and what is considered essentially toxic or above the recommended dosage. So a single nut is the recommended daily dosage. And if you're at a party and you see a bowl of mixed nuts, just remember that one Brazil nut is your recommended dosage, and a handful could potentially be toxic. So today I'm going to provide an overview of the properties of selenium, the reason for its importance, and ultimately why it's regulated. I'll highlight some of the chemical compounds that selenium can form and why speciation of selenium can form, and why speciation of selenium can provide insight into the pathway and potential toxicity. I'll also explain why speciation can provide valuable insight into some of our common problems associated with our existing total and dissolved selenium methods that most people are more familiar with for waters. So selenium is a naturally occurring metalloid, often found in metal sulfide ores. And being a metalloid, it exhibits both non-metallic and metallic properties. This is one of the reasons why it's so complicated analytically. So it's in group 16 and period 4 of the periodic table, and it has similar properties to elements above below and also either side of it. So sulfur and tellurium, and as well as arsenic, have very similar properties to selenium. Anthropogenic sources are typically from mining, power generation, so flue gas desulfurization plants, oil refining and agriculture, especially animal husbandry, where I mentioned about the fortification of certain foods and feeds, and also waste rock spoils, so associated with coal and uranium mining, oil refining, and smelting. They all have the potential to leach selenium, certainly if water and oxygen are present. So why is selenium important? Well, from a human health perspective, selenium is important as a micronutrient, and it is incorporated into amino acids, proteins, and antioxidant enzymes. Selenocysteine is considered the 21st amino acid. So deficiencies in selenium often are related to hypothyroidism, heart disease, and in some cases cancer. And recent studies have also shown that actually there is a benefit as well of adequate levels of selenium in protecting against both mercury and arsenic poisoning. But just as selenium has its benefits, it can also quickly become toxic. It's only an order of magnitude separates the tolerable intake level for humans and toxic effects. So tolerable intake level currently by the US EPA, and I think similar in Health Canada, is 400 micrograms per day. So remember the Brazil nut example, 1 is good, 10 would be considered toxic if you were eating that every day. Selenosis is the main critical health effect of chronic exposure to elevated levels of selenium. And the symptoms of selenosis include hair loss, nail deformities, weakness, decreased cognitive function, and gastrointestinal disorders. In the environment, there's also an excess of selenium has shown to be the cause of reproductive failures and abnormalities in egg-laying vertebrates, fish, birds, amphibians, and reptiles. And this reproductive failure is likely due to that similar chemical property of selenium to sulfur, in the fact that it's probably replacing sulfur in synthesis of sulfur-containing amino acids, such as selenocysteine and selenomethionine. So I'd just like to send thanks to Guy Gilron of Borealis Consulting for updating the next few slides and keeping me up to date on the latest regulatory developments in North America. So this slide shows the hierarchy and the degree of certainty associated with different sample matrices. So eggs and ovaries being the matrix of highest certainty in demonstrating a potential effect from selenium concentrations in the aquatic environment. So in Canada, it should be noted that first off, all guidelines we're typically talking about are based on total or dissolved selenium concentrations. In the case of tissues, obviously it's a total, and in the case of waters, it's normally either a total or a dissolved, depending on surface or groundwater. In Canada, the CCME still has a freshwater aquatic life guideline of 1 microgram per litre. Although Environment and Climate Change Canada and Health Canada have recently issued a whole body predicted no effect concentration, a PNEC value of 14.7 ppm for fish. And also the Canadian Nuclear Safety Commission, which currently bases their criteria on CCME. They also use a fish tissue-based threshold for risk assessments. And then provincially in Canada, we have most provinces default to CCME, but BC and Ontario both have their own guidelines. And very recently, Alberta has now adopted the BC values for both water and fish tissue that came into play in 2014. So these are the water quality guidelines for British Columbia in Canada. The freshwater aquatic life water guideline in BC is currently 2, and it has an alert set to 1, which is just, it's not really science-based, it's just half of the guideline. They have dietary concentrations for invertebrates set at 4 micrograms per gram, and sediment guidelines at 2. Both of these guidelines are currently interim guidelines. And then 2014 had some tissue, fish, ovary, and egg guidelines that were actually based and derived using what is considered to be a more appropriate approach, which is species sensitivity distribution approach, to come up with the values of 11 microgram per gram dry weight in eggs and ovaries, and 4 microgram per gram dry weight for whole body. Actually, only the egg guideline was derived using the SSD approach. From the US side of things, there was in 2016 a finalized US EPA criteria, and currently there is public review for a guidance document on how to use these values. In the States, Utah, there are values based on bird egg tissue criteria, which is quite unique. Kentucky also has a tiered approach. West Virginia and Colorado and some of the other states are still awaiting implementation of the new US EPA guidance document. There are a few others, but these are the US EPA limits that they're still awaiting a guidance document before a lot of the states are going to implement. But as you can see as well, there's these egg and ovary tissue guidelines, which are really the ones that are useful in predicting effects from selenium. Some of the other guidelines, as mentioned earlier, the Canada Climate Change is working on a proposed coal mining effluent regulation. This includes effluent triggers of 5 and 10 ppb, and also a fish trigger value of 14.7, as mentioned earlier. Health Canada also recently increased their maximum acceptable concentration in drinking water to 50 from 10. And BC Ministry of Health kept their guideline at 10 and did not change to the 50. And North American Metals Council has, Selenium Task Group has been proposing a third-party CCME water quality guideline revision. So selenium generally, as the inorganic forms, selenate and selenite, in water. Generally, it's this form that the inorganic form that it enters the food chain, and then bioconcentrates, most significantly the water at the base level, water to algae, and then converts into organic forms. So now you see where speciation can show you the pathways, and also because different selenium species have different toxicity, you can see how this could lead to making better decisions about selenium in the environment. So as I mentioned earlier, selenium concentrations and regulations are typically total selenium concentrations, or dissolved in the case of some groundwaters. And yet, obviously, the form of selenium will determine the potential pathway and also the toxicity. So just to give a simple analogy that one to, based on the similar chemical properties of selenium to other elements in its group and period of the periodic table, sulfur. Everybody's familiar with sulfate, so that's similar to, you could say, to selenate. Sulfate is obviously a fairly harmless species of sulfur, whereas as you increase and reduce sulfate to sulfite, and then eventually to sulfides and volatile sulfides, you eventually end up at hydrogen sulfide, which obviously is extremely toxic. And so it gives you a look at potentially the enormous array of compounds that can be formed, or species that can be formed of selenium, and how some of them are going to be more toxic than others. So let's take a look at some of these compounds of selenium. So as I mentioned, it's in group 16 of the chalcogens on the periodic table, and it typically has a valence of -2 in combination with hydrogen or other metals. Selenite and selenate are the predominant forms that make up the total selenium concentrations in water. Although selenium, elemental selenium, which selenium with a valence state of 0, can be present in particulate, and is typically less than 0.45 microns. So it actually can potentially go through filters, 0.45 micron filters. So selenite and selenate proportions in water are challenging to predict thermodynamically due to influences of biological activity, and they also have different absorption kinetics, with selenate displaying more similar properties to sulfate, being sticky, and is also the major contributor to total selenium in natural waters. So selenoscyanate and selenosulfate, those are two anthropogenic, although in actual fact selenoscyanate can be produced naturally, but typically produced from power processing plants, refining, when the fuel source originates from fossil fuels and oil. And also the main source of selenium used in biosynthesis is selenophosphate. So these are some of the common species of selenium found in water, but here are some of the less common selenium species. And again, it sort of shows you just how many compounds, gives you an idea of how many compounds could form. So organoselenium compounds generally are compounds that contain a carbon to selenium chemical bond, And selenium 2 is the dominant oxidation state in organoselenium chemistry. And as you progress down the group 16 column, the bond strength actually becomes weaker. And selenols are similar to alcohols, so replace the selenium with a oxygen, and thiols replace the selenium with sulfur, but they are fairly unstable in water. Then you have the diselenides, which are the selenium equivalents of peroxides. Disulfides will often oxidize fairly rapidly to dimethyl diselenoxides. And the sulfides themselves can often be detected from wetland treatment systems. Selenyl halides, again, unstable in water, but still could form. And then we've got the selenides, which are the selenium equivalents of ethers and thioethers. And they often oxidize to dimethyl selenoxides. And again, can sometimes be detected as volatile selenium species in wetland treatment systems. Selenic acids, they occur in some selenoenzymes, and such as glutathione peroxidase. So this gives you an idea of some of the less common ones. And then also we have some that are just organoselenium species that are found in nature. And selenium, as I mentioned, was an essential micronutrient whose absence from the diet causes muscle and skeletal dysfunction. But organoselenium compounds are required for cellular defense against oxidative damage and for correct immune function. So it's an essential micronutrient, as mentioned, for a host of mammals, birds, fish, algae, and bacteria. And so the selenium analog of cysteine is selenocysteine, and it's the 21st amino acid. And synthesis is also regulated by glutathione oxidase or peroxidase, which also contains a selenol group. We've also got selenomethionine, which is this is the typical form of storage of selenium in animal muscle tissue and plants. And some of these other ones are biologically, again, produced typically through the decomposition of some of the larger organoselenium compounds. So now to some of the challenges analytically that you can come across with selenium, and how typically analyzing for total and dissolved selenium differs from speciated selenium. So total selenium is often analyzed by ICP-CCMS, so inductively coupled plasma mass spectrometry. And in more recent years, collision cell ICP-CCMS, or what we call CCMS, collision cell or reaction cell ICP-CCMS are used and are very effective at removing some of the common polyatomic interferences. Chloride or chlorine is one of the ones that often used to affect selenium, and is now not really an issue with new collision cell technology. So most commonly, as mentioned, total selenium is used for regulatory compliance, and typically total selenium samples are collected in a 60 ml HTP bottle, plastic bottle. They're normally preserved to less than pH 2 with nitric acid. And then when they're received in the lab, they get digested, typically with a nitric acid, hydrochloric acid combination. And then they run on a collision cell or reaction cell ICP-MS. For dissolved selenium, samples are typically field filtered through a 0.45 micron filter, and then can be either preserved in the field or within 14 days in the lab. And again, the same instrumentation as total metals is used, but typically a digestion is not involved, as you would normally be trying to digest selenium-bound compounds and selenium-absorbed 2 particulates. So for selenium speciation, there are a number of different techniques. Originally, hydride generation coupled to various different types of detectors, sometimes ICP-MSs, sometimes AAs, atomic absorption spectrophotometers. But generally, they were dependent on chemical reactions to react with different species of selenium in order to separate the species. That added complexity and also limitations because it's not basing it on chromatographic separation, which some of the more preferred techniques use nowadays. So an example of chromatography separation would be cation-anion exchange columns or reverse phase columns coupled to an ICP-MS. They also could be coupled to a high-res ICP-MS and also a triple quad ICP-MS. And typically we refer to these as HPLC/IC -CCMS or ICP-MS. So it's a hyphenated technique involving separation using various types of columns and then detection of selenium using ICP-MS. Species quantified typically on the HPLC-CCMS are generally ionic, but there are also columns that will separate less polar species, things like selenium methionine and selenocysteine, and in some cases the volatile selenium compounds, so the dimethyl selenium and selenide and dimethyl diselenide. Also headspace, GCMS, so gas chromatography in this case is used to separate species, very similar to separating VOC compounds that you may all be familiar with. So typical gas station VOCs like benzene, ethylbenzene, they are also separated using this technique typically. So GC separates the compounds, and then the mass fragment is detected by the mass spectrometer. So these can also be used for detection of certain volatile selenium compounds. As in all these cases, typically the speciations are field filtered. So you are putting it through a column, so it would almost field filter it anyway. You certainly don't want to preserve them necessarily in the field with acid, because that may change some of the species. And so typically they're field filtered and collected. Sometimes they're chelated to just chelate some of the potential interfering metals in there. but most often for selenium speciation, they're collected in the field with field filtering, and then no preservation, and sent straight to the lab. So for most applications in water or tissues, using, for instance, an HPLC-CCMS, there's also a summation of selenium species, which should, in some ways, correlate to your total that you've got by a more traditional method for total selenium. But it is often the sum, including various unknowns, is often not quite what you'd expect, and so the sum of all these peaks that you could get, including this unknown peak that you see here, in many cases should add up to this total. But it also can highlight certain problems if it doesn't. So in waters, many species can be detected at sort of 0.1 microgram per gram level, and in tissues, we typically are detecting species down to about 5 micrograms per kilogram on a wet weight. And some of these unknown species that you can see in this graph, so this very first peak that you see come off as you're going from left to right, it's an unknown species. And this chromatogram is coming from a typical chromatogram from eggs. And you can see some of the selenomethionine is the large peak. That is typically how the selenium is stored. You can also see some selenium-4 and selenium-6, but you can see there are other compounds that are also unknown. And these sort of contribute to what I refer to as a sort of selenium gap. It's a gap, but it also gives you information, obviously, on what type of species might be present there, and also what you do and don't know about the various species that are in that sample. So often these, you can dive deeper and try to find some of these unknowns. And in some cases, if this unknown is a significant contribution, you obviously want to find out what it is. And so that's a continuous challenge for analytical chemists. And it's also something that certainly the instrument manufacturers are providing more columns that do allow this separation. And also you have quite a bit of information from the fact that you're running a collision cell MS. So you cannot just look at selenium, you can also look at other elements such as sulfur to try and figure out what this peak may contain. So from looking at this peak on an MS, you can also see whether there's a sulfur peak at that same retention time. And so you can get a lot more information from doing the speciation. So the differences that you do often see when you have some vast distances are often to do with biological samples or to do with biological treatment systems, where you seem to get all these breakdowns of other compounds occurring. So considering some of the multitude of selenium compounds, ranging from volatile compounds, selenium compounds, to proteins, it's kind of not surprising that there still are some unknowns out there. But certainly I think the analytical chemists are keeping up. So more importantly, speciation does identify many compounds which can be used to not understand the chemistry and potential toxicity of samples, but it also which also could lead to a better risk assessment approach. But it also is quite useful at identifying some of the challenges that you may see with regular total and dissolved metals analysis. So just to give as an example, a typical challenge we see with selenium samples from wastewater treatment plants and biological treatment systems is that dissolved selenium results appear higher than the total results when analyzed using the prescribed regulatory method. So we're using a nitric HCl digest, we're filtering the dissolved metals in the field, and for most other samples, for most other metals, you typically see the total being higher than the dissolved. But in this particular scenario, you can see that the influence sample has a dissolved concentration that is as expected. It's below the total. But something's going on with the effluent. So after treatment, something is going on. And the dissolved selenium is actually almost 5 times greater than the total selenium. So from the results in this table, we can see also the summation of selenium species from running it on an HPLC CCMS instrument, so using a selenium speciation instrumentation. And you can see that something involved in the digestion is causing this to be unusually high. And the reason is that this sample is undigested. This sample is digested, and these results are very comparable. So in this particular example, the initial reaction as well is to assume that you've just lost all your sample from doing a total digestion. However, the real reason is not due to that. The real reason, if you research literature and also do some internal studies, you learn the real reason is due to volatile selenium species. And what happens is they cause what's called a selenium enhancement effect. And they can sometimes enhance the selenium signal by as much as 10. In actual fact, some cases it's 20 and 30% of your selenium result. So this happens because you haven't performed a digestion, because it's a dissolved species. These dissolved volatile selenium species are going straight through to the instrument and are then massively enhancing the signal. It happens actually in the nebulizer of the instrument is where this all occurs, and you basically get this mass transfer effect, and it causes an enhanced signal. And the simple solution actually to remove this enhancement is actually to decompose the volatile selenium compounds by digesting your dissolved metals cut. And so by doing that, you will then see this dissolved number come back down to some level, hopefully below the total. It'll certainly be close, and it certainly won't be orders of magnitude greater than your total. So that's the first one of the first challenges, and again, just to prove that this was actually occurring, we did a little a study at ALS to demonstrate that the enhancement effects were due to volatile selenium compounds and not something else in that particular sample. And so we spiked some DI water with 73.4 micrograms of dimethyl selenide. And we set up several controls, and we also left an undigested but preserved sample for both 0 hours and for 24 hours to see whether the preservative would eventually break down the dimethyl sulfide like the digestion does. And so what you can see from this table, the selenium species present was the volatile selenium compound. And after digestion, you can see that in this case, you have an average recovery of 79%, but you have to digest the sample. You can see the enhancement that you can sort of see, so anywhere from 7 to 8 times the value of the original spike. And then you can also see that if you preserve it and then digest it, you also get a little bit better recovery, which may be to do with some volatile issues from not preserving right away, but still it shows that you get good recovery by adding acid in the field and also preserving in the lab when you see this type of volatile species being present in your sample. So obviously, speciation allowed, first of all, allowed us to determine what this peak was, but it also allows you to give better, a better way of looking at your actual whole sample and seeing what particular species could have an impact in the environment. Still at this stage, even though we're looking at the selenium speciation sort of told us that something was not quite right with the sample, we still didn't quite come up with a way of actually detecting what the volatile selenium amounts were. In this particular study, of course, we're adding just one species of selenium, and so we only need to detect that on a regular selenium method. But we were also interested in being able to determine what these unknowns were. And since we had many instruments already in our location in Vancouver that do volatile analysis, we decided to run the samples using Headspace GCMS and to verify that truly volatile selenium compounds were the cause of this. And so we're using just our regular EPA 5021 8360C, or what we call Headspace GCMS method. This just involves heating a water sample with various reagents in a sealed glass vial. We heat to equilibrium, and then the headspace from the vial is transferred into a gas chromatograph, and then the target compound concentrations are then measured using mass spectrometry. And we were able to analyze dimethyl selenide, DMESE as we normally refer to it as, and dimethyl diselenide at in this particular case at sort of nanograms, and in one particular sample micrograms per liter level. So this is this sort of peak we were looking at. We were looking for dimethyl selenide, we were looking for the 110 iron, and for the dimethyl diselenide, we were quantitating with the 190 quantitation iron. This is showing how you can't necessarily analyze everything, but it also shows that some things can be missed from some of the regular methods if you don't try and understand what's going on with your particular sample results. So typically detection limits for these two species for the sort of 0.1 microgram and 0.2 microgram respectively level. And again, a recommendation would be maybe not to use high density polyethylene container, but to use a glass container. Typically a glass perch and trap, which is similar to what we collect mercury samples in for a similar reason. So a glass perch and trap file with 0 headspace, and then preserved with nitric, or transferred to the lab from a regular bottle, and frozen at the lab before analysis. It's sort of the recommended way for you to analyze volatile selenium compounds. Another challenge with selenium samples from oil refinery wastewaters, and definitely from flue gas desulfuration treatment plants, is that you find the sum of the selenium species is significantly higher than the total reported. This is a more sometimes a more visual or a more obvious one to see, because often after addition of the preservative, you see a precipitate, and that precipitate is actually selenocyanate getting decomposed by the acid to elemental selenium. And sometimes you get a red precipitate, which is one of the allotropes of selenium, and sometimes you may get a black precipitate. The other problem with it is that metal that you've just formed will actually coat the bottle, and therefore when you take your aliquot for total metals analysis, it doesn't actually take any of that material that's absorbed to the container walls. So it sort of plates the walls, and you can actually see it visually. If you take a selenocyanate sample and add acid to it, you can see how this sticks to the container walls, and therefore isn't incorporated in the aliquot that you take for analysis. So there's two options available to sort of alleviate this problem. You take an unpreserved container and you analyze directly by CCMS, or once again you collect the sample in a 40 ml perch and trap vial as required for volatile selenium analysis, and you preserve with nitric acid. So elemental selenium just does not quite absorb to glass as well as it does to DPE plastic. So just in summary, so I hope I've demonstrated that HPLC-ICP-CCMS and Headspace DCMS can detect many common selenium compounds, but there are still some unknowns. Speciation can also provide invaluable information to better understand what's going on, understand bioaccumulation, and also trophic transfer, and to allow better risk assessment around selenium. And speciation can also be an invaluable tool to highlight some compliance issues associated with some of the regulatory prescribed methods, specifically around total and dissolved selenium and metals analysis. So thank you very much for your attention.
Wonderful. Thank you, Tim. We will go ahead and open it up for questions. Feel free to use your Ask a Question box or raise a hand feature, and you can ask your question directly to Tim at this time. I do want to let everyone know that this has been recorded. We will be posting it on our YouTube channel next week. All they need to do is search the ALS Limited to find our channel and then click on the North America playlist. You'll find a wide range of video resources and past webinar Wednesday presentations there. So we'll go ahead and give it a moment. Also, feel free to follow our showcase page on LinkedIn. We post future webinars and other valuable resources there as well. It looks like Guy just wanted to let you know, Tim, that he appreciates this presentation. It was very informative and helpful.
Thanks very much, Guy.
I do have a raised hand from Sarah, so I will go ahead and unmute you. Sarah, go
yes,
ahead.
do you? Oh,
no,
sorry
go ahead.
about that. Yeah, I was just wondering, so you have this for selenium. Do you have this speciation for any other metals?
Arsenic and antimony, you can use similar techniques. So we do actually do a lot of arsenic speciation for the giant mine up in Yellowknife, and also exposure monitoring, where you need to do speciation in order to truly understand the metabolites that are causing exposure. So yes, we also do methyl mercury speciation. So that's just the speciation differentiation between inorganic and organic mercury, and a very similar technique can be applied to antimony. So selenium, arsenic, antimony, and mercury are the ones we typically use this technique for.
Great, thank you very much.
We also have another question came in from Lori. She asks, when you analyze a sample for the Volatile study, what form of selenium species was spiked for the study?
Volatile selenium. So it's dimethyl selenide.
She also follows up with, when you use HNO3 to preserve sample, does this cause any change to the selenium species?
In this particular case, yes, it'll decompose the sample. It'll break down the volatile selenium, yes. So yes, definitely the selenium species would change.
All right. We do not have any additional questions at this time. She just does say thank you. I just wanted to let everyone know, again, we will be posting this online early next week. And we want to say thank you for attending, and thank you to Tim for this presentation today, and enjoy the rest of your week. Thanks, Tim.
Thank you very much, everyone. Bye-bye.